NASA's Dark Matter Files spacecraft has sent back its first message from interstellar space. For over 40 years, the spacecraft quietly journeyed through the cosmos, sending back data that most of us overlook. But now NASA is stunned by what it discovered. It didn't just drift into space, it uncovered something shocking at the edge of our solar system, something everyone ignored for years, a mysterious boundary, sudden changes in radiation, and new questions that challenge everything we thought we knew about space. What did it find, and why is NASA so shaken? A legendary spacecraft, surpassing expectations, launched in 1977 and originally intended to last no more than 5 years, 10 if the engineers were lucky. Dark Matter Files 2 has, against immense odds, survived for nearly half a century. It has faced the sun's radiation, cosmic dust, freezing temperatures, and the immense distances between planetary bodies. Despite these harsh conditions, it continues sending faint signals back to Earth, revealing secrets from the darkest edges of our local cosmic neighborhood. At this point, Dark Matter Files 2 has successfully followed in the footsteps of its sibling, Dark Matter Files 1 by entering interstellar space. It stands with Dark Matter Files 1 as the first pair of human-made objects to reach the boundary where the sun's domain ends and the true realm of the galaxy begins. Far from being a poetic phrase, this milestone is steeped in measurable evidence. Its instruments detected abrupt shifts in plasma density and temperature, along with spikes in radiation levels, all indicative of crossing from one well-defined region into another. The transitions occurred so quickly that it was as though the spacecraft had passed through an invisible gate, leaving the solar system's bubble and stepping outside into a galactic domain. What made the results even more intriguing is that these changes happened almost instantly, contrary to expectations of a smooth fade-out. The scientific community had believed in a gradual decrease of solar influence, but instead found a sharp line that is better likened to crossing from one room into another. This showed that the solar system may indeed have a more precise outer boundary than older models ever assumed. These abrupt data points also showed that right beyond our cosmic doorstep, conditions can become hotter in terms of particle energy, more radiation-laden, and arguably riskier for any spacecraft not built with robust shielding. Dark Matter Files 2 did more than just confirm the presence of a boundary, it also underscored how critical the sun's own bubble, called the heliosphere, might be. Previously, it was often thought that this region dissolved into the interstellar medium with no sharp edges. Now we know that there's a large jump in cosmic radiation and a notable change in the magnetic field once you cross it. This suggests that, at least in one regard, the heliosphere behaves like a shield. The second you step outside that shield, conditions shift profoundly, showing that space is richer in both energy and cosmic noise than was once believed. Scientists also drew attention to the surprising fact that the sun's magnetic field was nearly perfectly aligned with the interstellar magnetic field beyond. This flew in the face of many long-standing expectations and theories, prompting recalculations of how our solar system interacts with the galaxy at its boundary. The matter is complicated by the possibility that the heliosphere itself can contract or expand in response to solar cycles, meaning the boundary might not even be consistent over time or across different regions in space. Fast, sharp transitions and interstellar conditions. When Dark Matter Files 2 crossed this outer boundary, the most striking discoveries were the suddenness and precision of the changes. Data pointed to a sharp jump in plasma density, which revealed that the spacecraft had ventured beyond the zone dominated by the sun's influence. The temperature and radiation bursts also grew more intense, leading some to characterize this as stepping past an invisible membrane. It was not the sluggish fade that older textbooks had pictured, but more akin to opening a door and discovering a dramatically different climate right on the other side. Space scientists were astonished that these readings did not creep up gradually. Instead, the measurements changed so swiftly that it felt as if something like a cosmic threshold had been traversed. The scientific term for the edge of the sun's domain is the heliopause. What surprised many experts was the exactness of this boundary, which appeared more defined than predicted. The data implied that one moment Dark Matter Files 2 was in the solar system's environment, and moments later it was in a region shaped primarily by the broader galaxy. Beyond the heliosphere, galactic cosmic rays soared in intensity by roughly 70%. That enormous spike backed up the idea of the heliosphere behaving like a shield, filtering out a good portion of high-energy radiation before it reaches the planetary spaces we call home. In simpler terms, the solar system is enclosed by a functioning barrier that stands between us and the full onslaught of galactic radiation. Once outside that barrier, Dark Matter Files 2 was effectively unprotected, encountering an environment rich in fast-moving, high-energy particles. Additional revelations came from observing the shape of this boundary. Scientists had long envisioned the heliosphere as a bubble, but dark matter files 2*S crossing showed that it might not look like a neat sphere at all. Instead, its edges appear distorted, irregular, or pulsating. There is evidence to suggest that over an 11-year cycle, the Sun's magnetic field changes, causing expansions or contractions of this boundary. That could explain why dark matter files 1* crossed into interstellar space at about 119 astronomical units, while dark matter files 2* encountered it at about 121 astronomical units. The difference might not be random, but rather a reflection of a shifting, dynamic frontier. The idea that this zone might not be static but is instead alive in some sense gave rise to conversations about whether the heliosphere is just one part of a larger cosmic interplay. The longer dark matter files 2* stays functional, the more data arrives to refine our understanding of how often and by how much this boundary shifts. Unexpected details have shown up in the frequency of temperature spikes, fluxes in particle density, and changes in the magnetic field's orientation. Each new piece of data underscores the notion that things are far less predictable beyond the outer planets. Soon after it passed this boundary, dark matter files 2* effectively began to experience interstellar weather. This means changes in cosmic ray intensity, along with fluxes that may have roots in distant galactic events like supernovae or strong stellar winds from massive stars. Although the spacecraft isn't equipped to observe these events directly the way powerful telescopes can, its instruments can sometimes register subtle variations in particle energy or magnetic field shifts that hint at broad happenings in the galaxy. Why the heliosphere matters: the Sun expels constant streams of charged particles called the solar wind. These outward flows, along with the magnetic field, define a domain often referred to as the heliosphere. This region acts somewhat like a cocoon for our solar system, deflecting or dampening many cosmic rays that come from other parts of the Milky Way. High-energy radiation in the galaxy can pose real risks, including damage to spacecraft electronics or biological tissues. That is part of why the heliosphere is not just an astronomical curiosity, it has practical implications for space travel and our planetary safety. For decades, researchers tried to figure out where the solar wind effectively ends and where interstellar conditions take over. Initially, there were theories that the transition point would be fuzzy. The actual data from dark matter files 2, however, indicated a much sharper border than expected, with conditions changing over a relatively narrow zone. This was momentous because it meant the solar wind's ability to repel or slow incoming cosmic rays was stronger or more defined than earlier estimates. As dark matter files 2 drew near that region, scientists monitored the variations in plasma density, the speed of charged particles, and the orientation of the magnetic field. Each time, the data suggested the solar wind eventually reached a point where it collided or pressed against the surrounding medium, leading to a kind of boundary. Inside that boundary, the Sun's magnetism and